Testing. 1, 2, 3, testing. We'll start in 2 minutes time. If you have a question, feel free to ask. But otherwise, relax. And then we'll get ready soon. See, 1 minute's time. So let's get started. We're in between the public holidays, and it's very normal that people getting sick leave for today. So you see fewer people in the audience, but I hope this doesn't affect your learning attitude. But I guess it's a few people with a better learning experience. So what we do today is called random variable, okay? And of course, this actually may not be a very attractive name, but if you want to put it in a more business style, this is what we call probability modeling. So use probability to model some uncertain event, right? Because it's a mathematical way to describe things that we have unsure, like stock price or whatever you think the profit or the firm or how many customers comes in, so on and so forth. And then, of course, this will find the basis of how we do statistical inference in the second half of the class. So basically, usually if you take statistics 1, usually end up with this chapter, okay? And the second part will be the inferential statistics, which will be the second half of our class. So I think that makes sense why we learn this. Although we don't learn a lot, but if you really learn probability modeling, you go to advanced classes, they will learn various ways of modeling stuff, okay? But here we focus on the basics, but you will see the thing we learn will not be too much different from the advanced one. Advanced are, of course, more mathematical. But let's briefly review what we're doing, right? Because basically this is the topic that how apply our probability in the practice, right? Remember what's the name of class, right? Statistical decision based on this statistical analysis, right? So this is a random variable is the way how we apply probability theory. In particular, because we want to apply the usual math technique, so we know how to handle number. I mean, since our primary school, of course, we can do beyond number. I mean, if you learn math enough, you know, but the tools we learn in high school or in elementary school, in kindergarten are all numbers, right? Geometry, yeah, but most are numbers, right? We learn. So that is the reason why we want to, instead of working on set, which is this sample space or event, right? Seems, if you haven't learned that before, seems like to be foreign language to you, right? But now we go back to number. That make our life easier, okay? Random variable is a function or the mapping or what we call, right? You give me some event, I give you a number. So instead of talking about rolling even numbers, odd number, but we talk about, right, what the value the number can have. Okay. So just to recall the example we have here that is very important. Instead of we record ourselves the random experiment outcome are head or tail, we record number of head or number of tail, depend what you like, right? Then you, instead of head or tail, you record 0 or 1, right? By function, it means you give me something, I give you the other, right? So you give me the outcome of the experiment, I would tell you what the number to assign, right? So head, I would keep 1, tail, I have 0. So instead of a complicated sample space, I have a number there, okay? And you can imagine that as a measurement, right? With some way to measure our outcomes in the random experiment. By putting number there, then we can do a lot of stuff. And this measurement is well often used, right? We just care about the measured outcome, right? So for example, if you invest in the futures on the stock index, right? You don't really care about stock A goes up, stock B goes down. You care about in the aggregate, say Hang Seng Index or SP 500, is it going to go down, right? Because you buy the future is based on that index. You don't care about particular stock go up how much, go down how much. The aggregate index is you care, right? Or you invest in a portfolio, you don't care about stock A goes up or stock B goes down, or stock A goes up $1, stock 2 go up $2, or vice versa. You talk about the total return, right? Or invest in a company, you don't care about anything can change, right? Maybe number of employees could change, stock is bond can increase, is CEO can change, whatever, there are a lot of stuff. But at the end, you care about the stock price, right? Or how much the value of stock it is, right? The only thing you care, right, is the thing we try to put random variables on, right? And the good thing is if the single number, actually you can allow multiple number, but suppose you care about single number, this we focus on this class. When you measure something, usually there's some certain property that you can understand. And that is something we'll learn in the second half of the class is central limit theorem, which essentially said a lot of things end up it's normal. Bell curve would be enough to model all the stuff. And if not continuous, something is something like pros and con style of thing is more like the binomial. Or a rifle is like Poisson. So these are the things that when you change number, then a lot of way you can model is well studied, either from engineering or experiment that are very easy to understand. Okay, so it's the reduction from the outcome sample space to the number. And the good thing about this is you can put some mathematical structure, put some way how things are related, and then make some assumption, you can do some prediction, you can simplify, right? Because this is how you get from data, right? Because a model, right? We have some model assumption on this, again, we can predict what's going on, right? Making some structure that later you see, right? If we know this follow a particular bell curve, then we can make some statement about what thing can happen or not, right? But of course, why this particular bell shape apply to this scenario have to estimate from data, right? So basically what you're doing is at the end, the second half will be, we come up data, right? We simplify by model and the model will do a prediction. And regression is a way to simplify the relationship between two variables, right? And end up with a line. So this is something we'll learn at the end of the semester, right? So that would be the idea, right? A complicated data has very complicated thing, but you simplify for a mathematical model, right? And how to get the model is from the data, and use this data can predict, right? Just like you learn physics, right? You learn there are a lot of things, but you learn Newton's first law, second law, except the second law after equal to MA, right? Then you simplify a lot of stuff, right? You can add resistance, so on and so forth, those things in, friction or those kind of stuff, but you can make your life easier, okay? But anyway, let we go there, we'll make it more clear, okay? So here it's like you have pros and cons twice, right? You have 4 possible outcomes, but if you put in number of head, right? Then you reduce the free, right? Because you don't distinguish head tail or tail head, right? Just like I said, right? You have two stop, right? You don't really care about at the end of the day, right? Just how much you make, right? Just care about number of head. If you are trying to bet number of head, right? And that's the model, right? You can come from the sample space to the number, and then with some way to model the number, which one appear more often, because the left-hand side, you can say if your coin is fair, then it's equally likely, right? And then you can, but on the left-hand side, each number doesn't appear equally likely, right? So there's a cost of doing a number because not each outcome is equally likely, right? But also, if your coin is biased, not fair, each outcome is not equally likely, right? Then also affect the right-hand side as well. So everything will become more general, of course, at the expense of you can't distinguish the two outcomes, right? If you do, then the model will be more complicated, but we will do some simplification there, right? And same is the stock is continuous, okay? Just to remind you a bit is why we have two different tools is because of math, okay? And if you want to keep what you are using in the high school, discrete is fine. But there is some jump in the logical thinking when you become discrete to continuous. As I said, axiom 3 in the probability, when you apply to finite and to infinite, things are different. Okay, countable and uncountable is in the math is very different. You need some more tools to able to. Okay, but anyway, let's get started. Okay, now we're going to start our real business here today. So far, we have done just to remind you what's random variable. Just repeat once more: is to simplify the sample space. Instead of having an outcome for each thing that are unrelated, we have to measure the outcome space in some way, right? Say number of head, right? Some measurement there. And discrete means usually counting. You count how many, 1, 2, or 3, or 4. Easiest way to think. Okay. So how to describe a random variable? There are many ways. The most simple one is you tell me each number, how likely they are, right? The probability of each number, right? That's the meaning. Big P of x is probability that x, but x is a random variable, small x is a number, right? Say P of 1 will be x equal to 1, right? P of 2 will be x equal to 2. P of 0 will be x equal to 0, right? Big, for the capital letter, means random variable, right? The random variable can be any value, right? Before you do the experiment, right? But the small x are the numbers, okay? So sometimes you can look at a textbook that you call PF or PDF or PMF, whatever you like. So it's a little bit abstract. Give an example here. This is a very simple example. I have a head and tail, just toast once, okay? And suppose equally likely, 1/2, 1/2, okay? Then probability that x equal to 1, which is equal to head, is 1/2. So P of 1 is 1/2. P of 0 is 1/2. So basically you tell me for the random variable, according to which number, you put what number there. There's a table over there, all right? So the table here, okay, this guy, okay, is the probability function or probability mass function, right? For which number, you give me the probability, right? Remember, probability must satisfy 3 axioms. Each number must be between 0 to 1. Add up everything must be 1, right? And then the sample space is 1, right? Because a number is mutually exclusive, right? It's either 0 or 1, cannot be 0 and 1, right? So add up everything must be 1. So that's very simple due to axiom 2 and 3. Axiom 2 said the sample space is 1. Axiom 3 said adding up everything there, as long as mutually exclusive, that is addition, right? The sum of its part is equal to whole, right? And number is mutually exclusive, right? You cannot be, the random variable cannot be 0 or 1 at the same time, right? So that means that things have become easier, right? Axiom 3 is very simple, just add up, right? So that helps. That's why we don't have to twist our head to think about independence, those kind of things. It's much easier. Now the next is another way to describe, okay? And you will wonder why we do this, what we call CDF. This involves some adding, okay? So what is it defined is this CDF is called the cumulative discrete function, is asking what the big F is the probability that X less than or equal to X, okay? And you would ask why we do that, okay? That is a valid question, okay? The reason being that this will be same as integration in continuous random variable. And we want to learn it because we want to draw the parallel to the continuous counterpart, which we know how to handle. Later you will see. But this by itself in discrete is not something, by itself is not something, it's very important because you can always add something. There's nothing new there. There's no new information. But you will make a lot of sense when you talk about continuous. So we try to understand the continuous. Later you will see we draw the parallel there. So that would be more clear. But let's define it because there's nothing deep there. Okay. But let's see, this is not very deep. Okay. The reason being that the same question, the first one is know very well. Right? This we just talked, right? X equal to 0 means no head. 1/2 is tail, right? X equal to 1, which is the tail, the head case, is 1/2, right? And big F, okay, the big F is just very simple. You just understand in the primary school idea, okay? This is just go up and add everything backward, okay? Why this is 1, add everything up to here and go down, okay? It's 1, right? So why F of 0 is 1/2 is what is the X is less than or equal to 0, which only one case is 0, it's 1/2. What is F of 1 is probability that X is less than or equal to 1. Only two cases, 0 and 1. 1/2 plus 1/2 is 1. So that's the idea. Okay. Still, maybe you think, okay, this is a little bit abstract. But let me do a diagram. If you're a graphical person, it's easy. Okay. I have P of X I can draw in this bar chart idea, right? 0 or 1 have probability 1/2. Right? Do look that you stack them, must be 1. Okay. You stack everything there, must be 1. That's very simple. Okay. This Fx will be, this is going to be same here. You keep stack, 1 will be stacking everything before it. Okay. You're doing Lego. You do this in kindergarten, I suppose, or right? You put a wooden toy, you make a tower, right? Just here, lay down there, lay it out, like put this block on here. This is the one, right? That's how you do it. Nothing new, right? You learn in kindergarten, right? Add them up, the height of the tower, then it's 1, right? 1/2 plus 1/2, 1. Okay, there's nothing new here, all right? As I said, by itself is not very interesting. We learn continuous random variable. You will understand why we learned that. Okay, this still looks like why I do kindergarten stuff, right? But you understand this will be related to continuous. There will be something that we will see. Okay, don't worry about this. But just take it and then we understand. Okay. Now we are going to look at this particular example. Again, we will do kindergarten stacking toys. Okay, but this part shouldn't surprise you, right? You toss coins twice. The coin is fair. There are 4 outcomes: head, tail, tail. Okay, 4 outcomes is likely, right? And you record number of head, right? If 2 head, then it's 1/4, right? So that's why Px2 is 1/4, right? If 2 tail is 1/4, right? Then that's why P of 0 is 1/4. And head, tail, or tail, head equal to 1, right? X is 1. And probability is 1/2. So that's why P of 1 is 1/2. All right, so that's why this, I think there's nothing new here, right? This 3, I think it should be okay. Okay. The next part will be kindergarten time again. Okay. Big F of 0, which is initially what you have, is 1/4. All right. That one shouldn't be very difficult, right? Because this is just whatever you have now and before is here. Right? And what is F of 1? You just add whatever you have up until now, add together, you get this guy, right? 1/4 plus 1/2 is 3/4, right? And you ask what is big F here, F of 2, you just add whatever you have before, then you get 1, right? Just stack, 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 okay? The bottom is just telling you all the operation I have from definition, right? But operational is very simple. Okay, look at this diagram. This is simple, right? This should not be surprise you, right? Because we have 4 outcomes, right? These 2 outcomes here, 1 outcome, 1 outcome here, right? 4 outcomes, 1/4, 1/4, 1/2, right? And then here, kindergarten time, stack here to here. Get this one. Stacking everything before the last one. Is that clear? So I hope that you still remember how you do wooden plot when you're kindergarten. If you know, there's nothing, right? There's nothing deep in this diagram here, right? That's how P and F, right? But of course, you should be able to do the reverse way, right? If I give you the 2F, you can go back to the P, right? You just, this is this guy. The difference between the 2 is this guy. Different between this guy. So that's why these 2 are the same thing, right? This is the 2 sides of the same coin, right? Either you P and F. So what I want to say in particular, later you will see when talk about continuous, is there's no difference when describe the 2. You either do this or do that. Discrete, this is intuitive. Continuous, this is intuitive. Okay, later you will see why, but you will be very comfortable with this one. I mean, for now it looks like a little bit weird, but discrete, this is natural. Continuous, this is natural. Okay, you will see when we come back on Wednesday. You will see. Okay, hopefully we'll talk about the continuous type. Okay, this continuous random variable. Okay, so this one's a fair die. Simple. There's 6 numbers, 6 face die. Each outcome is equal likely. 1/6 for each one. So P is very simple. Every number have equal likely. Every number is 1/6, right? And F, kindergarten stacking, right? First step is 1/6. The second one is 2/6, 3/6, 4/6, 5/6, 1, right? If you're still not sure, here, right? Each one is 1/6, right? Now we do kindergarten stacking up, right? Here you stack, each step go by 1/6, right? So here I have some technical note to you is this description is not entirely perfect. Okay, this is okay for B school. Okay, when you go to stat department, they're very picky because a function, right? Function is defined on any number, right? So you have to tell them more complicated. The probability that x is equal to 0.5 is 0, right? So you have to be defined on its real number. So you have to say, this is a dot and this is a 0. But since we're not math class, so that's why this line is gray color. But when you go to stat department or a more serious math class, then they will have to demand you to write that. Okay, but we know math class, I'm not demanding you, but just let you know that we cut some corner when we do business presentation, right? You don't do this in a business presentation, right? Because everyone actually know, right? X cannot be 1.5, right? Cannot be 6.2, right? Cannot be -3. That's okay, we know it. So you don't have to worry about this. But you may be surprised when you go to stat department or math class or advanced class, they require you to be more serious about how you write your answer, okay? But you don't need to worry too much about that at the moment, okay, for our class. This adding up, I don't think there's an issue. And technically, it's a step function, the f, okay? But I'm not going to tell you about the left continuous thing. This is a step function indeed, right? But I don't want to go to detail, right? So as I said, everything in the gray color, just if you want to go study further. So what you have in your mind, this is sufficient, okay? I mentioned this is because of, in case you go to study an advanced class in stat, then you ask me, what, am I learning something wrong? No, because I simplify it, okay? Just make sure that you don't come back and see, okay, your slide is wrong, right? But yeah, I deliberately simplify it, okay? I know this is the case, okay? And you may remember it, okay? So now I think we have defined enough about the P and the F, right? P and the F, either way is okay. It's a complete description of what the random variable, right? Now we no longer have the sample space, right? The sample space become number, right? And probability that the random variable equal to which number is fully described by either P or F. Okay, that will be fine. Now we're in okay, no? Then of course, same as data. Okay, if I give you data, so what you're going to give me to tell me the data? All right, of course you can give your boss, this is a data set, you read yourself, okay, you will file tomorrow, right? So what you're going to do is you give the mean, median, or mode, right, as a way to tell your boss that this is what the data I know, right? And then next you give the variance to tell you that how accurate is this one, right? That's what you learn, right? You can also do skewness kurtosis. You can do the same exactly to the random variable, right? The random variable is fully described by the P or F, right? So if someone asks you how you describe this random thing, right? You give them the P, fine. Everyone should be very happy. But the problem is the boss doesn't have time, right? So what you want to give me a single number, right? Then it will call the expectation, right? That will be the mean, kind of mean of the random variable, okay? The mean actually is a weighted mean, but I would say more properly, but it's the mean. So basically what this expectation idea is very simple. Is remember, we have random experiment, we run it, there's an outcome there. The outcome can be any head, say toss and head or coin, toss and coin, head or tail. So what you're going to do, random variable will tell us what? This outcome, I record a number according to the random variable, right? Maybe 0 or 1 or 2, whatever number there, right? Then each experiment has a number, right? And here what is experiment means that if I run many experiments, right? Suppose I have 10,000 experiments, I have 10,000 number. Then this number data, right? How to describe data? Mean. What's mean of this number? Expectation, right? That's the idea. Let me repeat the statement. That's important because it actually connects to the topic one we learned. How you are going to summarize the data? Mean, right? So random experiment the same. Each time I experiment, there's an outcome there. Random variable tell us a number, right? And suppose I repeat this many experiments, I have many numbers, right? If I repeat long enough, right, this should be, the fraction will be very stable, right? And the average of this number is called expectation, okay? So that's what it is the definition will be called E of X, okay? The definition is, let's take this definition first and I explain, okay? Will be the value of the random variable multiply the probability, okay? If you do it seriously, this is just weighted average based on the probability. Okay, but let me define it in this appendix. Let's see this one. Okay, imagine you have a coin, fair coin. Okay, if the random variable is number of head, okay, number of head, right? So it's 0, 1. P of 0 is 1/2. P of 1 is 1/2. Okay. So you ask, okay, if you toast 1 million times, okay, roughly speaking, 500,000 is head, 500,000 tail, right? So then if you convert this head tail to random variable, that means that you 500,000 0, 500,000 1. Okay. So what's the average of the data you have? Is you add up 500,000 of 1, 500,000 of 0 over 1 million, right? Then 0 times 500,000 over 1 million is 0. 1 times 500,000 over 1 million is 1/2, right? That's probability, right? Because that's what random experiment is. You keep running this, right? This should be the same, right? Probability using the frequency approach is long-run frequency, right? Let's go back to here. So go back, that's all how we connect topic 1 or topic 2, right? The probability is well connected with the data. So that's why we have learned probability, right? The expectation is actually the mean of you repeat the experiment many times. Okay, this is what it is in general. Okay, we can prove it, but I'm not going to do the proof, but that's the idea there, right? So that means that if you told, the question is, what does that mean? 1/2 is an expectation, right? If you toss a coin, you expect half the time is head. That's what I mean, right? Or you can imagine if I have won this 2 times, I expect one of them is head, right? That may be easier, right? Those 2 times is one of them is head, one of them is tail, right? So it fit our the mean, right? This is what we call expectation. What we expect the number to be, right? It should be weighted by the probability, right? More probability, more likely. So that is the idea. Okay, this is a mu. That's why I use notation mu, same as the standard notation. Okay, and if you talk about stock investment, expectation is what we call mean return or expected return, right? What you expect the stock price to be, okay? You calculate it in this way, okay? Now, example is x can be 0 or 1, equally likely. So expected value of x is 0 of 1/2 times 1 of 1/2, 0, 1, right? So basically it's very simple, the calculation, right? When you have this table, it's very simple. You just multiply this vertically and then add horizontally, and you're done, right? So this table is very convenient to do all the calculation once of this table, right? Because as I said, P is a complete description of X, right? We care about X is that, right? And the expectation is a number that we care, right, about X, the mean, right? Okay, this is the finance application. The first thing you learn, mean return, right? Is how the return that you expect to get. Okay. Is that okay for this one? So in another example, because I think it's easy, I go faster, but if you think it's slow, let me know. I slow down in the break. Another example is roll a die, okay? Equally likely that 6 outcome, 1 over 6 for 6 outcome. Expected value will be, as I said, you multiply vertically and add horizontally, right? So that is nothing, operational is not nothing very deep here, right? Just multiply, 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 multiply. Once you do that, you add, then done. Okay. So the expected value is roll a die is 3.5. Okay. So nothing very deep here, right? Just definition, right? Just you give them a random variable, the P, I can summarize the information by the expected value. I hope there's nothing new here, it's just the mean, right? So it's supposed to have 6 million times, right? Each one with 1 million times, right? Just you calculate the average of this number. Okay. Now, we want to learn some property of linear property of the expectation. While you learn that, this will be very useful, especially when you go to finance class or you learn to do some calculation, which make our life easier. Okay. For example, X is the price of a single stock, right? And then suppose I model how the price move up and down by P, right? And one question is, I'm not only interested in investing one shares. Maybe I buy 1,000 shares or 10,000 shares, right? Then what will be my expectation if I invest in 1,000 shares, right? The good thing is, if you only care about expectation, there's no problem or focus on one single stock, because the expected return or expected price will be 1,000 of that, right? You don't have to worry about if you invest in 1,000 stock, right? Just multiply by 1,000. So that is the first idea, right? You don't have to separate model tell how to understand the shares movement or the portfolio movement, right? If you invest 1,000 shares, you just multiply 1,000 in expectation, right? So that's why in finance, you don't have to worry about how big the portfolio is if you care about the expectation, right? So that's why it is. The second one is also a good thing about investment. Imagine X is the stock, B is the bond, right? As a portfolio, I have X stock and B bond, right? Actually, I don't really care about the bond because bond is not going to change. The return is fixed, right? Assuming the bond is government bond, it's risk-free, right? The risk-free rate is very common in the investment, right? So that means that when things change, the X part, B is unchanged part, this B is not part of the thing changing, B is the risk-free, or the bond, you can separate them, right? The return of portfolio consists of stock and bond, right? With just the bond return plus the expected return of the stock, right? So that is very simple, right? And last part is just combine the two, right? You invest A number of shares in the stock plus B bond, just A times EX plus B, right? So in terms of expectation, right, you only care about the return, rate of the return. So that's why we only care about rate of return. We don't care about gross return, right? The rate of the return is important, right? That's why people ask, when you borrow money from the bank, you do investment, people ask, what is the rate of return, right? That's things we care about the investment, right? Because how much you invest will be proportional to this, right? It's proportional to the amount you invest. So that's the linear property. Everything is proportional in terms of expectation, right? So that makes things easier, right? So here is the price, right? Sorry, here is the price of stock, okay? Make it simple, the price can be 1 or 2 or 3, right? I make it symmetric, most likely it's 1/2, right? It's 1/2 probably is 2, a quarter of them will have $1, a quarter of them is 3, right? Suppose the current price is 2, say suppose, right? So what's expected value of the stock is $2, right? Which maybe makes sense, right? Because the price unlikely to move, right? Good news is 1/4, bad news is 1/4, right? And my son is keep calling me because he want to have more time for watch TV. Anyway, it's holiday for him because yeah. Anyway, just he keep asking me to allow, but I'm not allowing. So here is the question, right? I have a model for 100 shares. Okay? And what's expected return of, I have 100 shares and I have $300, right? So this portfolio will be 100 times of the expected return of the share at 300. So the portfolio value will be 500. Okay? Of course, this operation is only valid linear for the expected return. Later, when we return variance, which measures the risk, will not follow this formula. It is not linear. Linear only works for the mean expectation or the required return. Okay, later you will see it's different. Okay, but do note that this is very convenient. So our calculation of the expected return or the mean is same. Okay, no, regardless of how small or how big you're thinking about this. So we don't have to model separately. Okay, sometimes you have to worry about that, but expectation you don't have to worry. Okay. I'm not going to prove it. Okay. Now, before the break, we want to show you this one because this is the most interesting part, because finance, you learn the first class, the most basic tenet of the finance is risk and return trade-off, right? Because the market is efficient, right? If I want higher return, high expected return, right? I need to bear more risk, right? So that's the first principle, right? Is what you learn, right? There's no free lunch, right? That's what we learn from that. So how to measure the risk in probability, the easiest way is to focus on variance, right? How variation of the return is, because by construction, people hate variance, right? And that is human nature, right? You run away from danger because I don't know, then we're scared, right? I don't know because yesterday I go to Ocean Park. There's a Halloween festival. Then you got scared, right? The haunted house, right? At that time, at those days, you like this kind of fun, right? You want to be scared, right? But I don't think you want to be scared by your investment, right? If that's the case, you go to casino all the time, right? Some people do like, but most people we don't really did, right? So we don't want risk, right? We want to be safe, right? So that's why people get married. Why? Get married, the relationship becomes stable, right? For those who don't like you, who like risk, then maybe he never get married, right? That's fine, right? But most people want to be stable, right? Then they get married, right? So that is kind of this idea there, right? So as this variance, probably you will not surprise. It's same as if you run this experiment many times, right? You do this many times, you have many numbers, right? Variance of this number is exactly the same as this variance. So that's why we have the same name. So expectation is actually the mean. This variance of the random variable is same as variance of you do this experiment many times, calculate the variance, right? Same as toss a coin, right? You have many outcomes of 0 and 1. What's the variance of these numbers? There's the variance there. So the definition is a little bit tricky. Okay, not surprised is you take every value minus the mean square times probability, right? The probability is how many number of them, right? So let's give this example and then we take a break. Okay, that is nothing very deep here. Okay, so I have a 6 outcome equally likely. Each one is 1/6, right? And the mean is 3.5. We have that. If you can't recall that, 3.5 is from here. Since if you a little bit further away, see it, right? So once you multiply vertically and add them up, right? So we have that already. Okay. So how to calculate the variance of this random variable? Okay. What you do is you take every number there minus the mean and square, right? And times probability. Okay. So what you're going to do is not complicated. Instead of this, okay, you transform You take every number minus the mean, square it, and you multiply and add them all. Okay? Each number minus the mean, square it, and then times probability, and then add up. Will be around 3. Okay? Of course, if this is bigger, that means that the number vary more, right? Do you remember what variance is? It's how accurate your expectation is, right? And in terms of finance application, this one is smaller the better, right? We try to say in the finance theory, in general, the classical said you figure out the portfolio that will maximize your mean return expectation while keeping this variance as small as possible, right? You have two goals there, right? You maximize your return, also minimize the risk, right? And of course, there are some trade-off there, but maybe you want more return, you have less risk, but we try to figure out how is the optimal mix of the portfolio, right? But that's the idea there is the risk, okay? And after the break, we'll talk a little bit more, but there's some formula here, we'll talk about that after the break, okay? But you can see this is a risk measure, or accuracy of the mean. There's nothing new here because you already learned that in the topic 1, okay? Not my son, it's a random call. So don't worry about it. Okay, so I guess it's the time for a break, okay? And in the meantime, if you have any question, you can just stay here. I don't know if it's too fast or too slow. Please feel free to fill in. No, no, no. Yeah, you copy what you like. I want to copy, yeah, whatever you like. But there's no copy. You can copy how you do it. Important.
Professor, I know you mentioned it's okay if you can use a calculator on the test, but can you use it like a graphic calculator for the homework?
Whatever.
Okay.
Unless I calculate that right step. If I don't have even know it. No. That's right.
All right, thank you.
I cannot go. You're not that. All I want you to do is myself. I cannot say I use it. I don't use it any other.
Well, yeah, I took a stat class at my other university. We couldn't even use the like us for like Q and stuff. Like I was trying to like on home.
No, I don't want to do it. It's but only things.
Oh yeah, yeah. No,
I don't want it.
all right, thank you.
So learning, it's not you don't care about yourself. There's no way I can care about.
I appreciate it.
Yeah. Oh.
Were you in the restaurant? Oh dang. Appreciate that. Great talking.
it's a mu. Okay, sorry. Thanks for, so we'll quickly review the variance of this formula, right? So just this one, okay? So what we want to do is this, the variance formula, right? So just what we do is, I don't know, I cannot do annotate. Okay. So it's this one minus 2 and square, and this is how you get this number. And you multiply by this thing and do the same, right? So the question is, if the price X is represent the price of the stock, okay? And the stock can be $1, $2, or $3, right? And you have $400 cash. What is the risk measured by variance of the portfolio? The variance of this whole thing, the portfolio, because of cash, at 300 actually is not there. And 100, you take it out, become 100 square. Then you multiply that. The risk, if you measure by variance, is 5,000. Okay. Of course, you will say this number is not, meaningful, but you later you will see you try to find a good mix of these two, right? To taste your need, right? Because different amount of investment will lead to different expected return and different risk, and you pick the right one, okay? Right? Because that is how you choose your investment level, right? Not going to talk about the math here, okay? So here I would just very briefly mention something that we touch a little bit. We don't go to formally, but it's very often we describe the world not just a single random variable, right? If we buy futures, then probably, then it just Hence the index, just single number enough. But sometimes we want to choose out of two stocks, right? Or even if I choose stock and bond, bond can also have variation, right? Maybe bond is the company go bankrupt, you lose it, right? It's not completely risk-free. Or you want to invest in two different stocks, how you want to split among two possible investment, right? In that case, you need to map to two numbers, right? For example, you toast two coins, or you toast a coin roll a die, right? Then you have to do it, right? Or you go to horse racing, right? I think you can bet 3 of the horse race outcome, right? If you win 3 of them, then you win a lot of money, right? And that would be something that we care, right? If you know how to do 2, actually you can go more generalize to any number, okay? So why we want to look at more than 2 number, okay? And if you want to describe that 2 number x and y, okay, the same here with the probability p function that tell me that for each possible value of the random number x and y, you have the probability, okay? And I'm not going to talk about the p and the f, okay? What I want to talk about is this result, which I don't prove, but probably is obvious to you, is if I portfolio of stock and bond, okay, X is stock, Y is bond, what is this portfolio return, okay? And the answer is satisfy linear property. I can divide and conquer. I can only look at what is the return of my stock and what is the return of my bond. I can do it separately. I don't need to combine when I talk about the expected return, okay? The mean return of the portfolio of with stock A and stock B, I can separate, investigate. Focus on stock A. What are possible value? Look at the probability, multiply. A done. Stock B, do the same. Add together, I'm done. Okay, I don't need to focus on the whole portfolio. So this is the return of how to do that. Suppose I invest A share in X, B share in Y. It's just A times return of the price of each stock X and B times each price of each stock Y. Okay, so for expected return, life is easy. Everything's linear. Okay, that's good, right? But the troublesome part is the variance, the risk. Okay, the risk. So consider the case which we would do in the beginning is if the stock and the bond, suppose they're independent, right? Then the variance of the portfolio will be just sum of the risk of individual investment. So we can do divide and conquer if they're unrelated. Okay? If the two investment in your portfolio are unrelated, the risk of the portfolio is simply the sum of the risk of each part. Fair enough, because they're independent, right? But of course, if you remember, independence is very difficult requirement for investment, right? Because suppose two shares, two stock is hardly unrelated, right? Because macroeconomy do good, they move together, right? Covariance is hardly zero, right? So usually, this is not the formula we use. The formula we use, we will come back later. The formula we use is you have to calculate covariance, which is the same idea we have before, right? If you have each possible outcome, you have two numbers, you can calculate covariance of two, right? You can do random experiment, X and Y, and then this is the formula, which we don't ask you, but this is the formula you will learn in finance class, which is the variance of portfolio with X and Y will be sum of their individual plus how they're related. That's why I learn covariance. Okay. And why we care about this? Remind yourself, covariance can be positive, but can be negative. What does that mean? If you want to minimize your risk, your investment should try to figure out things that are unrelated or they go in opposite direction, right? That's why they call safe asset. Why people do cryptocurrency? Why people do buying art? Why people buy antique? Why people buy gold? Why people buy yen? Because they are unrelated to the US stock market, right? Because people tend to think the US stock market is the one that people should invest, the largest stock market in the world, right? People try to find things that are or go the opposite direction of the US stock market, then you have some premium. But people are willing to pay to reduce your risk, right? So that's why people want to do diversification. That is the reason we do diversification, right? Diversify, right? Because covariance is the variance times the correlation coefficient, right? Just reverse it, right? So that's why you want to figure out assets that are unrelated. Okay? I'm not going to talk about that because talk about those will be beyond the scope of a class because they're investment class, right? So just give you some idea of the portfolio, just a little idea, okay? So I have stock X, okay, and stock Y, okay? Stock X has mean return of 0.1, variance 0.05, okay? And Y is 0.5 and variance 0.01, okay? Now consider the case I have how to get this number, historical data, okay? How you get the 0.1 and 0.5 from historical data. And then you want to look at the return of the portfolio. Suppose half of the money you put in X, half money put Y, okay? And then your expectation of the portfolio will be half of expectation of X and half of Y, right? So half of 0.1 and half of 0.05. That is your expected return of the portfolio, okay? What is the cost of doing so is the risk. Variance of that, okay, is half of X, half of Y, okay? And because they're independent, I make the simple case, the independent, you just add them up. If not, you have the covariance, okay? And you can see here is difficult part here. 0.5 squared because of variance. You take it out, it's squared. Okay? And add up, it's this number. So simple question for you would be, I invest half and half, right? If you change this number, maybe 1/3 to X, 1/3 to Y, you have different mean and different variance. Okay? So if you do an investment or financial planning or investment analysis, your goal, of course, is to decide what's optimal weighting. Right? Investment is to look at the efficient portfolio, which try to look at which mix would better suit your need. Right? Of course, I omit the covariance here, right? But the covariance there, then you will figure out what is even more complicated, right? But that's the main idea of the investment, right? To figure out that given the structure of mean and variance, how to figure out the mean variance efficient portfolio, right? But this is what you learn in investment class. I think it's a required class for the B school student, but I think later you will learn that part, okay? But this idea behind, before you do it, but I'm not going to go into this detail because then I will destroy your incentive to go to that class, right? So I left that for you for that one because it's not, we're not investment class, right? But that would be the idea of the risk and return, right? Because that's why you learn expectation. So only if the independent variance of the sum is sum of the variance, only if there's no covariance. And if the covariance, then you have to look at how they related, right? Because if one move up, one move down, then they cancel out. Average out is less variation, right? Because that is the finance, right? We try to combine different assets to reduce the variation, right? That's what you said, right? Don't put all the eggs in the same basket, right? If you put the same egg in the basket, the covariance is 1, right? You want to reduce the correlation because covariance with the correlation, right? You want to find the covariance or correlation is 0 or negative even. The negative is even better, right? So that's why crypto is so highly demanded because you expect the crypto is unrelated to the risk, right? Is that clear? Is that okay? Because let me review what we've done so far because we go to a more concrete thing. Okay. So what we learned together with last class is we are going to more deeper in the probability theory and focus on the case where the future is summarized by a number, which is random variable. Okay, it's number 1, 2, 3, 4, 5. Okay, or the stock price, right? And given that, if number, how to describe this number can be is by the probability function, which is P of X, or the same thing, big F of X. Okay, they're the same thing, but two-way description. Okay, to describe the random variable completely, is by P or by F. Okay, they are kindergarten stacking exercise or unstacking. You stack the P become F, unstack the P become unstack the F become P. Fine, and then P is very complicated. You can imagine if 1,000, we can have 100,000 number, all right? So that's why we don't want to look at this complicated thing. We look at two number that is our focus. One is the mean, one is the variance, same as the data, right? The mean is expected value. The variance is the variance, right? And mean is what? You apply in finance is expected return. The variance is the risk, right? So I don't think there's anything new here, but just the way we frame it, right? Because expectation is same as you repeat this experiment many times, or the number FHO, right? The very same idea here, right? Now, we are going to have more fun now, right? Because now we equip ourselves with the terminology. Now we go to the fun part. That is called the probability modeling. Because this part is we can directly apply because this is the part that it will be very useful. And this is the part that even though you don't run regression, you don't run anything, this is the model that will be applicable to many, many scenarios. Okay. So let's start with some toy example here to make you feel what am I modeling. Okay. So the most simple model, which actually we have been using all the time, is assuming each possible outcome is equally likely. Right? Each number, it can be there. It's like, let's toss a coin. 0 or 1 is likely. Or a roll a die, 1 to 6. Each outcome is likely. When you use this is when we know what are possible, but we don't know what number can be. That is the first way to model unknown situation, right? I don't know what number can be, right? Maybe I think, say, suppose today, what is the Hang Seng Index? Okay. So Hang Seng Index is now is what? Hang Seng Index now is, whoa, so fast. Now it's already 21,000. Okay. So uniform distribution will be saying that, okay, maybe I expect tomorrow will be equally likely between 20,000 to 22,000. Each number is equally likely, right? With like 2,000 possibility, each outcome is likely, right? You forget about the common places, right? So that is uniform. You give a range. Within this range, it's equally likely, right? So that would be, you don't know, that's the best to predict, right? So that would be the way to do the modeling, okay? And say, so example, in the example here, this is how you draw, right? You don't know, but you know what a possible value. You assign the same probability for each one, right? Suppose this is, you're guessing how many customers are arriving in next hour for your restaurant. Okay? Or how many defective product you can have when you check the inventory. Suppose you check 5 inventory or 3, suppose you check 3 sample, right? Then it's 1, 2, or 3, right? How many customer? Actually, I should have 0 if I have checking inventory because they can 0 defective, right? So that would be equally likely is the way to do, right? It need not be 1, 2, 3, 4, 5, can be 0, can be negative, can be a number, right? So this is general that how you make the thing, okay? So this is the thing that you would try to model when you don't know what's going on, right? So, and of course, I don't talk about that, but this is how machine learning works. Usually, you know what are the outcomes. You assume uniform. You use the base rule to update this and keep learning, update, and this thing will be the thing that that model will use. It's actually you will combine this with base rule and come up with a nice model. Right? Start with initial model is uniform. And then you keep learning the model, keep feeding the data there, you keep update, and this model will become nicer and nicer and nicer. That will be base rule. But we're not going to talk about that, but that will be the idea of probability modeling. Okay? Now we look at another example, which we call the Bunoni distribution. This is the, I would say, the cornerstone of probability because it's actually the beginning of the probability. Okay, and what we learn for the rest, for the discrete, will be based on this one. Okay, Bunoni is very simple. You just look at the world with 2 possible cases. You consider either success or failure. Just 2 ways to look at the world: either success or failure, or either it's okay or not okay. A or B, okay? It's bipolar, okay? So the prediction is very simple. Failure is, success is P, failure is minus P, okay? Outcome 1, outcome 2, 2 possible outcome. We call One outcome success, one outcome is failure. Okay? We call success probability P, failure is 1 minus P. P can be 1/2 or can be any number. Need not be 1/2. Okay? So 2 outcome. Okay? So this probability of 1 is P 0, 1 minus P. Okay? So our model, which we call, is described by this simple model, right? X can be 0 or 1. Okay? Probability is 1 minus P or P. And whenever you think the outcome is binary, okay, then you can model this, right? You can say penalty kick, right? Is in or not in, right? 2 outcome. And right, so that is the idea. Okay, we will generalize this, but this is the most basic foundation. Now, here comes a crazy starting case, come crazy. Okay, here is the thing that I remember when I learned this, my head twists a little bit. I bang my head to the wall several times before I understand this. I hope you don't have this problem. Okay. So how can I write Px? Okay. Now you can see the Px is completely described by this, right? X is 0 is 1 minus P. X is 1 is P. Okay. How can you get a formula for that? Okay. Well, because they're completely different thing. Okay. So mathematician, I don't know how they do that, but they bend their head, okay, to get it. P raised to the power x, 1 minus P raised to the power 1 minus x, right? You will see, okay, what's this? It's crazy. I understand you because when I first learned that, it's crazy. You never understand why it's the case. But this is they play around with math, okay? So x equal to 0, okay? Say x equal to 0. What does that mean? X equal to 0, the first term is P raised to 0. Anything raised to 0 is 1. Right? So it's 1, nothing there. And 1 minus P raised to 1 minus 0, that's minus P. Right? What we want. And if x is 1, P raised to power 1 is 1. The second term, once P raised to 1 minus 1 is 1 minus 0, 1 minus 1 is 0. So that's gone. So exactly this guy. Okay? So this is a compact way to write this only. Okay? And then you ask, hey, is it you're crazy? You're doing something crazy? Yes, we're doing something crazy. Okay? Why this will make sense is later introduce binomial, the next one, this will make sense. Otherwise, I mean, no way to write this complicated thing, right? Because this is what we have, right? Why we have to bend our head to do this, okay? Why we have to write this acute weight, right? Why we have to make it up in this form? We will know very soon. But I hope you accept when you have 0 here, this is 0, this is 1, become 1 minus P, right? The same as this guy. Okay, this is a mathematical trick to write in this way. Okay? Now, the mean of x is P. Why? Because this is 1 minus P times 0 plus, because how you get expectation, right? Is this multiplied by this, which is 0, plus this multiplied by this, which is P. So that's why it's P. Okay? And variance, you can check. I'm not going to tell you. It's P times 1 minus P. Okay? But so the variance, can I draw a graph? Oh, yeah, I can draw. That's good. So this one, oh, nice. I can draw a graph. I'm very happy now. P, this variance P. Okay. Now try to recall what you learned in the high school. What this graph looks like. Right? This one would be like this. 0, 1, you have a Monday blue. Oh, I'm not doing good at this. Let me do it again. Your Monday blue is a sad face. Yes. is this shape, and 1/2 is here, and this 1/4. It's very simple because when P is 0, this variance is 0. When P is 1, P is 1. Why is the case? Let's think about this. Why the variance is 0? When P is 1, that means that always success. All right? What's the variance? No variance because everything is successful. When P is 0, everything you do is fail. Right? When P is 0, yeah, everything you do is fail. Right? So there's no variance. Right? We repeat this assignment. So only when P is 1/2, that has the highest variance. Why? Because your half success, half failure. That is, you have bunch of 0 plus of 1, right? So that's why it's looked at this shape. Okay. So this will become very important later, but this is the idea behind this. Okay. Of course, this is still something very terrible. Why we care about this? Because x only equals 0 or 1. There's nothing new here. Okay. By itself, this is not very useful. Is that okay to hear right now? We will talk about. Is that okay? I mean, if you first learn this, this will be a little bit. You cannot easily accept this. Don't worry, we'll repeat next class again. But let me continue. But we'll continue this again. So don't worry about it because this is how we learn. We learn random variable is to say, okay, we give you some definition. What the P looks like, what the property they are, and how to apply it. Okay. And so far, we cannot apply it because this is still so stupid. Okay. Now, you can draw a graph like this. If P is 1/2, then look like this. If P is 0.3, then look like this. If P is 0.8, look like this. But there's nothing new here. Okay. Now we come to the most interesting one. Okay. Just to remind you that one thing I forgot to mention, Brunoni, okay, is a name, right? I think a French name, French surname. And Brunoni is he actually is not one guy. It's the 3 brothers, and 3 of them is have a contribution in probability. Okay, so Brunoni family actually do a lot of probability theory. Okay, but anyway, we're not going to interest in history, so we just skip it. But let me go to this one. This is the I think it's the most important thing here. Okay, this is the binomial distribution. Actually related to the binomial combination we learned in the last chapter. That exactly is used here. Why learn combination? It's because here. Okay. So now we have more fun because instead of looking at the Brunoni trial, just success or failure, we repeat this n times. But independently. Each one is independent. Okay. That means that I try one up to n. Each one I have the same experiment. I repeat n times. What I care is how many number of success. That's what I care, right? Why we care about this, right? Because maybe this is modeling the marketing effort, right? I meet the first guy. How likely are I going to make the sales, right? So I have meet n customer. How likely every day, then how many sales I'm going to make, right? Or you can imagine this is very useful in engineering, right? You have a plane, many engines, right? Each engine have different failure way. Then you calculate how many engine will fail during the flight. And then you have to decide the system, how many engine have to be okay in order to plane to be safe. Right? So that would be the idea, right? This is why this is very useful. Okay. And later you will see this build all the foundation later in Poisson, all the ideas behind it. And Poisson is the best way to model process. But then we will talk about that next class. But quickly, okay, don't worry about that. We just give you the idea. We'll go to more detail next class. That's the idea. Okay. Just I have a success or failure, but I read n times. So it can be no success at all, or all success. So it will be n plus 1 possible value. First is 0, no success, up to n, right? So that is the combination here. NCX is here. So, and then you have Px 1 minus Pn minus x, okay? This formula is something I try to explain today as well. But what I'm doing here, okay? Actually, same as your assignment here goes on. You have n experiment, you ask x of them successful, okay? And n minus x is failure, okay? If they're independent, that's what I said. If you have first n success, first x success, n minus x failure, if they're independent, you can multiply each one, right? First success, second success, up to x success is p, and 1 minus 1 minus p, right? That is all success and all fail, right? But this only one way to do it, right? But you can have first n minus x failure and x of them success. Or there are many ways to do it. Hamilton way is NCX. Why? Because imagine you have n different balls. You draw x of the balls. The ball you draw means that one successful. That is NCX. Okay? I will go back to this again. Okay? But when we end this, okay? This is the figure model n, okay? Turn out to be, not surprisingly, the mean of this random variable is n times p because they're independent. Okay? And the variance is np times 1 minus p. Okay? I will go into detail next class of this random variable by binomial because turn out this, later you will see, this is the discrete version of bell curve. So if you think the bell is you learn the normal, the thing is standard, this is also very standard. Okay. Right? Because you can imagine, to make it simple, you can imagine, okay? Suppose consider height, right? Height or IQ or weight is dependent on many factors. They're independent, right? Suppose your gene go this way, you get you higher. If you go this way, it doesn't get you high. So your height determined by all the gene, whether you click this button, right? Is how much success you have depending on your height. So that's why you can see the height of human society follow the bell, right? Or your IQ is following whether your brain, you have this cell, you have this cell, you tick, right? Which cell, whether you have tick, is a random process. So that's why this is, you can say, I would say, is the bell curve in a discrete sense, right? So that's why this is so important, because you imagine this is the good way to model a lot of stuff. Okay, and if a lot of things, if in discrete, binomial would be a good fit. Even though itself is not following binomial, but you can assume this is a good model to model the bell, discrete bell. Okay, or you can imagine this: how many customers come to your store can be modeled by a bell curve, right? Or how many people cheat in the exam, maybe follow a bell curve, right? Or then that is actually very useful technique there, right? Because maybe each of you is going to cheat with probability 1, the probability 0.01, right? How many people cheat in my class? Then is adding everyone up, right? And then whether you cheat is dependent on others, then binomial is a good approximation, right? Or how many people will fail my course, right? If probability is 0.01 and you multiply by n, then it's determined by this, okay? But don't worry, this is the most important thing, so that's why I'll repeat next time. So I'll repeat in October, means Wednesday. So enjoy the holiday. I'll see you on Wednesday. So don't worry, we'll come back to this again, okay? I'll say I want to answer any question you may have.